lab 5 for physics. So this is the world's largest rope swing lab by myself, Manfilos Bonavicius. So in this lab, the purpose was really just to analyze the motion of the rope mass system, which was the person just swinging, and it's oscillating in an arc due to it being released at an angle from the vertical. And we're pretty much just looking to see, like, the end goal of this experiment was really to see if energy is conserved. So the setup was releasing the person so that they begin swinging back and forth and oscillating, and you do that just by jumping off of the actual natural structure. So Newton's second law and the energy principles were used, and we used a theoretical simulation by using GlowScript to model this. So we're just observing and predicting a person's motion and change in energy to see if it followed the energy principle. So Physics Explained, we have a lot of different equations here that were used along with some other ones. So the force of gravity we know is mg, net force, change in momentum over change in time. So the spring, rope, and gravity acting, so it was kind of just like counteracting that. So the tension in the rope was kind of acting like a spring in this case, and so we were able to use that. Then we have the net force equation written down with the equation for the force of the spring along with force of gravity and the change in energy principle, which shows that energy is conserved and is really just the work done by surroundings plus Q, which is also equal to change in kinetic energy plus change in spring potential energy plus change in gravitational potential energy, of which those formulas are written on the side to the right. But other formulas used within this experiment and lab were velocity update formula and position update formula. So the assumptions of the model were that the person weighs 70 kilograms. We just used this just because it was the average weight of a person. The video angle keeps changing, but for the most part, it's like a side view and like head-on view. There's no net force acting in the z direction is our assumption. The length of the rope was around 47 meters. Initial conditions were a velocity of 0 at the start, with the initial position being 47.25, or the length of the rope. And then the spring constant we found to be roughly 11,000 newtons per meter, just because that's what Google said for a climbing rope. And the system was just the person rope earth system with surroundings being nothing. So pretty much we just looked at the video and had to base everything off of that and every piece of information that they really discussed. So you can see them really just like jumping off of the thing. And then you can also see how he's strapped onto there, which is why we're just assuming he's like a point mass kind of moving around on that rope. So GlowScript code, there's a lot of code here. Obviously, I needed to update it. Well, not update it, but like write it out. So I had to add in all the different initial conditions, which going back were, let me do this. Which the initial conditions were the 70 kilograms, the length of the rope, which was 47, and then pretty much just using different equations that we had for the energies. So we had to plug in the delta U of the spring and stuff like that, delta U of gravity, and all the different equations, like 1/2 mv squared and all that. And eventually this allowed us to create a model, which we could use to actually, model the situation that we had. So what we ended up getting out of that was some graphs showing the position versus time and showing the change in energy along with the motion. So the leftmost picture right there is just showing how the model demonstrated that it was like swinging back and forth. The position versus time is just showing how it is really oscillating back and forth. The position keeps going back up and down. And then the change in energy is showing that really no change in energy. So the predicted graphs and what actually happened generally the same. Possible error was just other forces such as drag, which we didn't account for, but also like the average weight not actually being 70 kilograms. And then what does it mean? Pretty much, was the energy principle satisfied? And we said yes, just because we assumed there was no external forces acting upon it, and the model shows that there's no change in energy. However, in real life, there would be drag and there would be a negative change in energy of the system. But